So today we're doing a continuation of the basic integrals lecture. That's what happened last time. Last time we introduced basic integrals. The premise was that the fundamental theorem of calculus changed everything. Under the right conditions, the signed area under the curve would just be the antiderivative evaluated at the endpoints. So that made the antiderivatives incredibly valuable. Incredibly important. So important that we changed the notation. We do away with the limits and we call this an indefinite integral. And then we set out for this lecture and the past lecture and the next few lectures, we set out to do nothing but become really, really good, or the best that we can be, at finding antiderivatives. That's the name of the game now. And so we studied the very, very basic ones, the ones that appear on the basic sheet. Let me see if we can pull out that sheet. That's this sheet right here. The ones that appear here, we call these basic because if you just look at the right hand side, if you have to do the antiderivative, all you do is look at the left hand side, and there's the antiderivative. That's why we call them basics. Here are some examples. The the integral of e to the x. Well, that would be easy. That would just be e to the x plus a constant. The antiderivative of cosine, well, that would be easy. That would be just sine x plus a constant. If you don't believe me, you can check. What's the derivative of sine x? Cosine x, I told you. The antiderivative for the power rule family of integrals, all you do is add 1 to the power and divide by the new power and add a constant. That's what we call basic ones. What we want to do today is take it up a notch or two. And really, you should know that there's about maybe 8 or 10 different techniques for finding antiderivatives. But we will only do 1 or 2, maximum 3 in this class in Math 150. The standard outline just calls for 1 or 2 of these techniques, where the rest of the techniques are supposed to be taught in the second semester calculus. Okay? So we'll just be happy learning 1 or 2 techniques. The one we're learning today is called U-sub, the U-sub method of integrating. Okay? And it's really easy to explain. The name tells you all. All you do is make a substitution for u, more or less. So let's practice. Let's take this excellent first example. The integral of cosine 5x dx. Imagine if it didn't have that 5 there. If it was just plain old cosine x dx, we would call that a basic one and we'd be done with it. The antiderivative would have been sine. But it's got that 5 and you wonder, is there a way that we can get rid of that 5 or do something about that 5? And what we're doing today, the U-sub, is exactly the method for getting rid of that 5, roughly speaking. Let's do it. I'll make a little dictionary here where I will translate from x's to u's. This is a U-substitution. I'm going to make my u set equal to 5x. This is a dictionary. Okay, between u's and x's. By making that dictionary, that means I can have an equal exchange rate. Every time I have a u, I can exchange that for 5x. So this becomes the integral of cosine, not of 5x, but the cosine of u. And that's significant because now it looks a lot better. Cosine u du, except for the fact that these don't match. And so I've got to also figure out a way to replace my dx. So I go back to my dictionary and I ask, well, okay, I got u and x, but how is dx related to du? So I have to, expand my little dictionary here. If I slap a d on both sides, d on that side and d on that side, I would get that the du is worth 5 dx's. The 5 can come out through the d. And so this gives you an exchange rate. Every time you've got a du, you can exchange that for 5 dx's. Or, said differently, every time you have a dx, you can exchange that for 1/5 a du. Okay, that's perfect because I've got a dx here that I need to exchange. And this tells me exactly how to exchange it. 1/5 du. And so I continue here and I say, okay, this is cosine u. And instead of x, dx, I'm going to have 1/5 du. Right? There I've made my substitutions and I'm ready to roll with this because then the 1/5 can come out through the integral. That was one of the famous properties for integrals. And all I'm left with is cosine u du. That's what we call the basic one. That's the one you practice. I posted those homework problems, maybe 50 or 100 of them, because they're so important. You've got to be good with the basic ones. I can't tell you how important it is. You got to be good with the basic ones. So assuming that you're good with the basic ones, this would become 1/5. The antiderivative of cosine would be sine u plus a constant. Of course, it's customary to answer the question in the same language it was asked. The question was asked in x's. The answer we've provided here is an answer in u's. So it's customary to go back to the dictionary and figure out the change it back to x's. So every u can be exchanged for a 5x. I'll erase this. So, whoa, not that much. I'll erase this so we can have just what we had before. Before we had that u was equal to 5x. That was the exchange rate. So I use that exchange rate, u is equal to 5x, to change it back, and I'll be done with this. This will be 1/5 sine 5x plus a constant. There you go. That's our first u substitution. After you do a bunch of these, you get the good feeling for them, and you may not have to write every single step because you understand the steps so well. For example, had this been a 7, after you've done a few of these, you realize that, well, this would have been 1/7 sine 7x. Had this been a 13x, this would be 1/13 sine 13x, etc., etc. Alright, let's try another one. Got to practice a lot of these. Whoa, there you go. What do you know? It's a 7x. So here we go. You make a little dictionary, and you say, alright, I'm going to make my u is equal to 7x. I know I'm going to need my dictionary with the dx's, so I'll go ahead and slap a d on both sides. Du is equal to 7 dx's. By the way, if you just write something like this, du is equal to 7, you're totally wrong. You got to use a chain rule. You can't have a little part of the dictionary here where you have du's on one side and no d anything on the other side. Unless there was a constant, and that would be 0, but that usually won't happen on your u substitutions. So usually a hint that you did it right is if you have a du on one side and dx's on the other side, such as that. Okay, now I've got my dictionary. I'm ready to roll with it. So this would be the integral of cosine of u. My 7x can be exchanged for u. And the dx can be exchanged for a 1/7 du. And that 1/7 can come out, so that would be 1/7 times the integral of cosine u du. And this is a basic one now, so this would be 1/7. I know this because I've done my homework. Sine u plus a constant. You're basically done, except it's customary to answer back in x's, so you would substitute sine of 7x plus a constant. There you go, your second u substitution. Pretty easy, huh? Yeah, they're not all that easy. We're just learning to walk before we can run. Take a look at this example, an exponential example. Suppose you had e to the 3x dx. That 3 is the part that bothers you, because if you're a beginner, if that 3 wasn't there, just imagine, if that 3 was not there, that would be a basic integral. The integral would be e to the x, and you'd be done. But look at the magic. The 3 is there. So what are you going to do? Easy. What's today's section? U sub. So we make a little dictionary. I'm going to make my u. This is the only tricky part, figuring out what to make your u. I could make my u e to the 3x. I could make my u dx. That would be a little crazy. I can make my u a lot of things. The obvious one here would probably be to make u equals 3x. And a lot of times the choice is not so obvious, and so that's where practice comes along. You got to practice a lot. And if you get it wrong the first time, then what you got to do is just give up and start crying. Don't try a different u, by all means. No. Just start crying and give up. Don't try a different u. I'm just kidding. You should try all the u's that you can try and never cry. Alright, that completes my dictionary. I've got my u's and my du's. and then I see how that pans out. If I get an easier integral in the language of use, then I've succeeded. If I get a harder one, I'm going to go back and change to, alright, I got a dx here and a dx here. What can I exchange it for? I believe I can exchange it for a third du. That's the exchange rate. That would put me at 1/3 integral of e to the x. No. That would put me at 1/3 integral of e to the u du. And that's nice, because this is a basic one. The antiderivative of that would be 1/3 e to the u plus a constant, which can be further simplified or exchanged. The u can be exchanged for 3x plus c. There you go. And it's easy to check. If you take the derivative of this, think about what would happen. You'd have e to the stuff. The derivative of e to the stuff is just e to the stuff times the derivative of stuff. So that would be e to the 3x times the derivative of 3x. That would be e to the 3x times 3, which would cancel that 3 and get you back exactly that form right there. Right? Told you. U-substitutions. You can do U-substitutions. Here, again, this is an obvious one. Because if that 3 wasn't there, you'd be done. Just imagine, if that 3 was not there, you'd say, well, that's a basic one. Secant square x dx, that's tangent. But guess what? That 3 is there. And so it proposes a nice little challenge. How to get rid of it using your little dictionary. What do you think you should make u equal to? Well, the obvious choice is 3x. Then du would be 3 dx, and that sets up the exchange rate. I would turn this into the integral of secant square u times my dx is worth 1/3 of a du. That would be 1/3 integral of secant square u du, and that's a basic one. So that would be 1/3 times tangent u plus a constant. Again, it's customary to change back to x's, so that would become 1/3 tangent of 3x plus a constant. Can't believe I get paid to do this. Insane amounts of money. This stuff is so easy. I could do it with my left hand. I could do it with 2 fingers. It'd be called math fingers. Math 2 fingers. That's how easy this is. But I'm just kidding. They get a little bit more interesting. How about this one? This one proposes a nice little challenge, or some options here. One option would be to take that 3 and FOIL this out. You know, you should, maybe you could be thinking about something like this. You might be thinking, hey, maybe I can do this. 2x plus 5 times 2x plus 5. FOIL that out, and when you're done, multiply times 2x plus 5. And that'll get you a long, pretty little mess here. But each piece would be easier to handle. In fact, I've done it here. Hey, does this remind you of those cooking shows where they show you how to cook and then they pull out the thing and it's already cooked? That's what I did here. You'd FOIL this out, and when you're done, you get this. Voila. So good. And each of these pieces would be really easy, because for each of these I could just do the power rule. And one of the basic ones that we did learn last time. So this would be 8x. I add 1 to the exponent and divide by the new exponent. This would be 60x. I add 1 to the exponent and divide by the new one. This would be 150x. I add 1 to the exponent and divide by the new one. Plus 125. If there's no x, I add 1x. Add 1 to it, divide by 1. You're done. There you go. That would be one option. Of course, it's kind of a silly way to do it, because it requires you to FOIL this out, and that could be very unelegant. The U-substitution proposes a different idea. It says, hey, you know what? Wouldn't it be nice if this was just u? Wouldn't it be nice if instead of having all this stuff, you just had u to the 3rd? Wouldn't that be nice? And a du? That would be nice, because it would just be power ruling. You'd be done. You'd be u to the 4th over 4, and you're done. Maybe we can set up a little dictionary like that. Let's see how it goes. What if we make u equal the quantity 2x plus 5? Well, that would force du to be 2 times the dx. Right? Stop me if I'm lying. Am I lying? No. that's its popular dictionary, and I can translate, and now this becomes integral of u to the third, and instead of a dx, I can exchange that dx for a half du. See, because I could divide both sides by 2. This would mean a half du is equal to dx. That's the exchange rate. And this could get me the 1/2 to be pulled outside. That would give me a u to the third du. Oh my goodness, that right there, that's duck soup right there. That's a basic one. So that would be equal to 1/2 times u to the fourth divided by 4 plus a constant. And what is that equal to? Well, that would be 1/8 u to the fourth plus a constant. And what is that equal to? Again, it's customary. Replace back your u's. So it's 2x plus 5 to the fourth plus c. And there you go. You know what's interesting is to note that if you were to FOIL this out, 2x plus 5 to the fourth, if you were to expand this binomial expansion, you would get exactly the same as this, except the only thing that might be different is the constant. But who cares? It's a constant anyways. I've got a constant here too. It might be different, but who cares? But the expansion here would be exactly the same as that one. I'll just check the first one. Look, the first one here is 2x to the fourth, right? Here the first one would be 2x times 2x times 2x 4 times. That's 16. 16x to the fourth divided by 8. That's 2x to the fourth. I told you. It's interesting to note if you were, this right here is the same as that, except possibly for the constant. Anyways, that's a part of a larger family. All these things that look like some stuff here raised to some power, they're variations of the U-substitution that we just did. Here it gets really, really crazy. You know, imagine expanding this to the 21st power. You'd have a huge, long thing. If you wanted to expand that, you might want to leave that for like a slow weekend when you don't have anybody to go out with, no friends. You might try to expand that to the 21st power. For us, we got better ideas today. Today we use a little bit more elegant thinking. We say, hey, you know what? We're going to make a little dictionary here. It's going to start off with setting u equals x minus 5. If that's part of the dictionary, then the other part of the dictionary would have to be that the du must be the same as the dx. They're interchangeable. Slapping a d on both sides. And this translates to the integral of u to the 21st. This is my u to the 21st. Whoa, what? dt, no. Whoa, I did this on purpose just to show you. Every time your x's and your t's, if they don't match here, forget about it. I can't even use the dictionary. I got way too many variables here. Forget about it. We don't have enough information to do that one. See, I was just testing you guys. But, I'm just kidding. I made a typo. But it's probably instructive. Let me start over. But not edit this out. Yeah, it's really, really important that these match. If they don't match, forget about it. I think I talked about that last lecture as well. So let's do this. Let's clear the page. What if we had the integral of x minus 5 to the 21st dx? So I was saying before I was teaching that other lesson about the variables matching, I was saying that you could make a U-substitution. U is equal to x minus 5, then du would be equal to dx. Then this would turn into the integral of u to the 21st, and then dx could be exchanged for a du. And now what do you call this? Duck soup. This is a piece of cake. Standard basic one where you do the power rule. The anti-power rule. You add 1 to the power, that would give you 22, and you divide by the new power, that would give you 22, and you add a constant, and yippee-ki-yay, you're done. So this would become x minus 5, the quantity, to the 22nd power, all over 22 plus c. Or you could expand that if you want to the 21st power. Hey, who am I to say? Who am I to judge? Alright, want to try one more? Let me pause this for a second. So this one looks a little bit more interesting. You could try a lot of things on this one. And I won't try the easiest thing because it won't be as instructive. Let me try something else. Suppose I make I got a lot of choices for u. I could make u equals the square root of x. Here, I could make, I'm going to tell you all that I could make u equal to the square root of x, or maybe u is equal to the square root of x plus 1, or maybe u is equal to x to the 5/2. All these choices are feasible. Maybe they all work, maybe none of them work. I don't know. But you should not be afraid to try them. You can't not go up to bat because you're afraid to strike out. That's not what we do. That's not what we do in this country. We go up to bat even if we strike out. So let's try something, alright? So let's try, for example, the square root of x. If I try the square root of x, that's the same thing, by the way, as saying u is equal to x to the 1/2. Okay? Then I gotta complete my little dictionary here. Du would be equal to 1/2 x to the negative 1/2 dx. Right? If I did that correct, you bring it down, you subtract 1, and then you do the dirt of the stuff. And now let the substituting begin. The only creative part is choosing the right u. This is not that creative. You got to take the derivative, and substituting is not that creative. All you do is substitute. So the square root of x, I'm going to exchange that for u plus 1. Oh my goodness, that one. Wow. I'm afraid of that one, so I'll just take baby steps. I'll kick the can and do it later. How about the dx? The dx would be, let me think, look at the dictionary. The dx is equal to 2 times x to the 1/2. I'm bringing stuff over there. Du, that's equal to dx. This is just algebra. It's all for dx. So I've moved the 2 over there. I moved the x to the negative 1/2 over there. It became the x to the positive 1/2. That gives me an expression for dx. So I can exchange that dx for this quantity. So I will. So this would be times 2x to the 1/2 du. Make sure I did that carefully. 2x to the 1/2 du. Okay? I've never done this problem before in my life. I'm doing it live. Okay? I think is more instructive. Excuse moi. So then what happens? Let's clean it up. Just a little cleanup here. So this will be the integral of u plus 1. Oh, I could take that 2 out, way out there. That 2 can come out outside the integral. And then I've got x's here. I've got x to the 5/2. I reckon I got x to the 5/2 plus 1/2. That's 6/2. I think that's 3. Du. Oh my goodness. Now what? X to the 3rd. So what? X to the 3rd. I gotta go back to my dictionary now. See, I postponed that substitution. There's no postponing now. I gotta get rid of the x's. I'm not done translating until I've gotten rid of all the x's. I only want u's. And then I will make a judgment whether or not the new integral is easier than the original one. If it's not, then I gotta go back and use a different u. Or just cry and give up. But if it is, then I've succeeded. But at this point, we're not done. We've got to translate, keep translating. Never give up. Never surrender. So I got my dictionary here. I'm going to play with my dictionary right around here. So this tells me that from here, I'm going to go from here. This tells me that u squared is equal to x, right? If I square both sides. I'm trying to figure out what x to the 3rd is. Well, if I take both sides to the 3rd power, that would tell me that u to the 6 is equal to x to the 3rd. And that gives me a nice little exchange rate coming from the dictionary and telling me that x to the 3rd can be exchanged for u to the 6th. So I come over here and I go, this would be u plus 1 x to the 3rd u to the 6th du. You say, whoa, 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 now what? I could distribute this in there, distribute it, and that becomes 2 times the integral of u to the 7th plus u to the 6th du. Right? And now I can break, and I break it up into 2 pieces. So this would be 2 times, I do this piece first, u to the 7th. That would mean u to the 8th divided by 8 plus u to the 7th divided by 7. And I could add a constant. I could add it in here or out there. It doesn't matter because multiplying by 2 wouldn't change the fact that it's still a constant. So then I cleaned it up. Oh man, I don't know if you guys can see. Can you guys see? Let's give it some more room. Yeah. Alright, that's enough. So then let me think. I gotta substitute back my x's. So this would be 2 over 8. Instead of u I have what did I have? I have the square root of x. So x to the 1/2 plus this is 2/7. 2/7 times something to the 7th plus a constant, and again that would be this x to the 1/2. And now I'm done. Now I have completed the substitution, and we're good to go. Okay, pretty nice, huh? Audacity, just keep using the dictionary. This is a nice problem because it shows you that there's no need to be afraid. You just keep using the dictionary until you've substituted all x's out of the problem, and then make a determination whether that's easier than the original one or not. Here though, it's interesting to know that so many different ways to do this problem. Here's a much easier way, but of course if I had done it this way you wouldn't learn as much. This is all about learning, it's not really about doing the problem. I don't really care what the answer is. But I do care that that was instructive, and I do care that there are many ways to do it, and I do care that here's another one that you could take a look at. You could take this and distribute it. See, Bella likes this one. Easy. All the integrals Bella could take, so she left. You could distribute this and say, well, that's x to the 1/2, right? I could say this is x to the 1/2 times x to the 5/2. Well, that would give me, how many x's is that? That would give me x to the 3rd plus x to the 5/2 times dx, right? That's just distributing. And now what I've done in this case is I've cut it up into easier problems. Because this is sum, you can do each piece separately, right? We've done this before. X to the 3rd dx. We'll handle that piece separately, and we'll handle this piece separately. We'll make two little problems, or two littler problems, two smaller problems out of the original one, and see how that goes. This is just standard power rule, the basic one. X to the 4th over 4. I would add a constant, but I've got another one coming here, so I'll save my constant. This would be x to the 7/2 all over 7/2 plus a constant, and you're done. This would be a nice way to do it. Perhaps nicer, but not as instructive. Today we're practicing U-substitution. So the other way helps you. The other way we just did it helps you practice the U-substitutions. And it's easy. It's nice to note that this would be equivalent to that other answer we got not too long ago. Pretty nice, huh? Want to do another one? Let's do it. I think I can do 2 or 3 more. Then I'm going to go with Bella. Let's set up a little U substitution here. So I would make U equals 3x plus 7. If I make that my U, then that would make du be equal to 3 dx. And that would turn the integral into 1 over u, and instead of a dx, I would have, I could substitute it for a 1/3 du. I've had a lot of 1/3 in this lecture. That's just an accident. It's all about the dictionary. You could pull out that 1/3. That would leave a 1 over u du, and that's a basic one. That would be 1/3 ln u plus a constant. Again, that's assuming that u is positive. Okay, or you have to take the absolute value here. Clear? Pretty nice, huh? Oh, let's do this one. This one looks interesting. This one I would make a little dictionary here. By the way, not everything in life you can do using the U-sub. Most integrals you cannot do using the U-sub, but there's a lot of them that you could, such as this one. I would make u equals tangent x. If that's the case, then du would be equal to secant squared x dx. And isn't that convenient that I have exactly that expression right here, this expression, secant x dx? Because the little dictionary tells me that I can exchange that for du. So this would become integral, and my tangent I can exchange for a u, so this would be u to the 7th du. Right? And the rest of that is boring. What else? How about this one? I would make my u is equal to sine t. If that's the case, then du would be equal to cosine t dt. And you look at that and you think, well, isn't that convenient that I have a cosine t dt there, which is exactly the right exchange rate for du. That would make this integral e to the u, and this part right here can be exchanged for a du, which of course would be e to the u plus c, which of course would be e to the sine t, and you'd be done. And you can take the derivative of this, check it, and you see you get that, because the derivative of e to the stuff would be e to the stuff times the derivative of stuff, leaving you exactly that. Alright, last one. Integral of tangent. You might think this is a basic one, but you look through the basic list and none of these have, I don't see tangent here, tangent here, tangent here. None of these are tangents, so it's actually not exactly a basic one. However, we could write it this way. We could say, after all, tangent is well known to be the ratio of sine of t all over cosine t, right? And once you write it that way, it's sort of suggestive of the idea that maybe you can do a u-sub. Maybe you can make u is equal to cosine t. Yeah? If you did that, what would the derivative be? That would be negative sine t dt. Right? Let me make that more clear. Sorry. So I'll make in my u is equal to cosine t. That would make my du be negative sine t dt. Say what? Now what am I going to do with that? Alright, I see here a cosine t. That would be my u. And I see here, very conveniently, look at this, very conveniently, you see that part right there? Sine t dt? That's the same thing as this part right here. What can that be exchanged for? Oh my goodness, again, that should have been a t. See, it's almost time to end the lecture. dt, that sine t dt can be exchanged for a negative du. This is the right exchange rate. A negative du is equal to a sine t dt. That's perfect. That would lead me to the following conclusion. On the bottom I just have u, and on the top all I have is du. Or said differently, 1 over u du. Now that, my friends, that's famous. That's right around here. Right? Isn't that this one? The 1 over x dx. So this becomes, that becomes ln u plus a constant, or ln cosine t plus a constant. There it is. Anybody who somebody knows, the antiderivative of tangent is, of course, natural log of cosine. Okay? I think we should end it here. Alright, again, I can't stress enough how important it is for you guys to actually do the exercises. I could do a million of these. But that's not nowhere near as instructive as you actually sitting down and doing them with paper and pencil. Nothing but your noodle power, a little pride, and hopefully you guys get the hang of it.